I'm now going to give an introduction to the topic of reinforcement learning. So there's some good recommended reading. In particular, there's a book that really stands out to me, and it's basically Reinforcement Learning by Sutton and Bartow. All I will say is don't use the first edition. It uses a slightly out-of-date notation for things. The second edition uses a much nicer way of writing down relationships, for example, probability of the next state and the next reward given past state and action and things like that. It uses this nice probability way of writing things down. So let's first of all think about, what is involved in reinforcement learning. And basically it's to do with having an agent, which is something which can make actions and look at the state it's in. It's about how this reinforcement learning agent can learn to do the best thing. How can it make the best actions by interacting with its environment in order to achieve a long-term goal. Now this agent's going to be running with no supervisor. There's nobody telling it what to do. It's just trying things out, and sometimes it gets positive reward, sometimes it might get negative reward. And it's got to learn on the basis of trying out lots of sequences of actions and working out what was the best thing it should do when it's in a given particular state. Generally, though, that the actual feedback you can get in a reinforcement learning system can be very much delayed. So you don't just get feedback immediately relating to the reward. It could come several steps along the line. So you have to make a series of actions before actually you see any value in any of them, in fact. As I said, this is quite often done certainly initially by trial and error. You just try something out. And when we look at these situations, we're going to look at simple mazes where the actions are just going to be moving around and the environment is unknown. So there's lots of different kind of examples of systems that we can think about as being part of the reinforcement learning kind of frame. One of them is these one-arm bandits. This is a one-arm bandit, and in this particular kind of system, the idea is to pull the handle appropriately, and if you're lucky, if you pull it, you might find that you actually end up getting some money back. Games can also be considered very much reinforcement learning problems, in as much as you have to make an action, take an action, make a move to beat an opponent, and if you win, then that's you get your reward in terms of winning the game. We can also think, though, in terms of robotic systems and how they can also make use of reinforcement learning. So robotic control is certainly something that can be done using reinforcement learning algorithms, and a good example of this would be, how do you keep a pole balanced up? And to do so, what you need to do is you have to learn, given the state that the cart is in and the angle at which the actual pole is, what's the appropriate action to take? You've either got to move left or right at a certain speed, and you've got to do that in order to keep the thing balanced. You can also use reinforcement learning to learn, for example, how to keep a quadcopter stabilised as well. And the thing we're going to be looking at most, because it's a nice clean example and it's very classical in terms of, that's how lots of these algorithms are explained, it's in terms of mazes and grid worlds. And the idea is going to be, how do we get from a state to a rewarded state, which could be, like the way out of a maze. So let's think about the example of noughts-and-crosses. The idea is we just got to make sure that we put our move in the right place, and the overall game idea is to win, right? You'll make a move, then your opponent will put down something, and then you make another move and put down your cross or whatever it was, and that final aim is to gain reward by winning the game. And this will consist basically on making a series of actions, and then you observe what's happening, and then you make another action, and then you observe what's happening, and then you make another action. Like I said, Gridworld, or moving through a maze, is an example that we're going to use a lot in this course in order to explain the concepts. And the idea would be, In this case, it's quite clear what the states are. They're just going to be sort of almost like the numbers representing the individual cells on the maze. And you'll be able to take certain actions. You could either move north, east, south, or west. Not when there's nothing on the other side. You can't move west if there's nowhere to go. You'd bounce back, but you can certainly move in that. If you're in state 1, you can certainly move to 2. And you'll get a reward as well in these grid worlds when you get to finally move into a state where there is actually a value associated with it. So, for example, here all the states 1, 2, and 3. If you move between them, you get no reward, but then you finally get a reward if you move into this R state at the top. People have played games like TD backgammon, that's temporal difference backgammon. That's just one of the algorithms we're going to look into, and you can learn how to do that playing reinforcement learning. That was done quite a long time ago now. It's quite a few years ago. The idea is, in this case, we want to estimate, what's the state value. You've got a certain state of the board, and you want to know how to choose then the next action which gives you the best possible chance of getting a long-term reward. And initially you'd start off randomly playing, and this particular algorithm, like I said, it's a very old version of a game playing algorithm, was played millions of times. The system then could learn the value of the states, and then it could learn basically in order to make an optimum action in order to gain as much reward as it can. We spoke about this before, but basically a really nice example of deep Q learning was the one done by DeepMind, which basically plays video games, Space Invaders, and it was just looking at the state of the system by looking at just the visual image of the screen. That gives it its state. It gets a reward by looking at the score. That was also explicitly made available, but the idea is just on the basis of the state and the long-term, in terms of the reward it gets after an action, run this loads and loads of times, and it was able to learn to move a joystick appropriately in order to actually play a very good game. In fact, it's much better than humans. So reinforcement learning then is the science of taking action. Really, it's the science of making decisions as well, right? So we have to decide, do we move left, do we move right, up or down. There's also continuous space reinforcement learning and continuous action reinforcement learning, where we might actually decide to make a value in terms of a movement rather than a discrete movement as well. But always the agents interacting with the environment, they're always made in order to get the best possible long-term goal. So it doesn't care about the immediate reward, but it cares that it's doing the right thing. So it finally, let's say, gets out of the maze. So, what action should the system take in the given state in order to get the best long-term reward? And actually this sort of field, this particular technique covers a lot of fields, right? There's stuff in computer science which would come under the umbrella of machine learning. That could be machine learning. Even optimal control is really very much related to reinforcement learning. In neuroscience, people are interested in how the reward system in the brain works. There's sort of dopamine neurons and stuff in there that seem to do similar things to systems based on reward. Psychologists look at classical and operant conditioning. Economists look at rationality and how do you make rational decisions. Engineering and academics sort of look into, and mathematics look into things called operation research, how to make decisions in big organisations. Okay. So what is the agent? Well, the agent is the thing. It's almost like I said, almost like you could be considered an agent, and this agent's basically something that is able to look at the state of the system, take an action, and then basically look and see what the new state is and look and see if it got a reward for the action. So the agent is basically something that can look at the state of the world, take an action, respond and actually see what reward comes back from it, and then hopefully notice what the new state is. So whether or not we can see all the states or not is a question of observability, and we'll come to that a bit later. there's different ways of actually making the decision on what action should we take, right? There's systems which actually learn the value of a state using a value function, and there's other systems which directly learn what's called a policy, so they directly learn what action to take rather than learning the value of a particular state. They learn in a state what is the action we should take. So there's value-based and policy-based methods. There's also a mixture of both, actor-critic, which use both of these. They actually make use of a value function and also a policy. So here are some sort of slightly more well-defined definitions. A reinforcement agent will use a policy. That's basically, it's represented in this kind of form, pi a given s. So it's basically just saying, in a general sense, the probability of an action. What's the probability of an action given the state? And this policy lets us choose the action given a state, right? So if we've learned a policy and we know the state, we can put it into this equation and it will tell us the probability of which action we should take given the state. It could also be deterministic, in which case it would just tell us one action that we should take. But the idea really is as follows. Then the agent basically can observe the world. It hopefully knows what state it is, or can estimate what state it is. It then takes the action it thinks is the best one, at least when it's in a learned system, and it can observe the reward, and then it gets, again, an update to the state. So the way that would work then is, to start with, the agent will be in a current state, right? It uses the policy in order to generate an action given the state we're in, which is pi a given s. This basically moves somehow the agent's relationship with the environment and leads to feedback, which can be then seen from the environment. And the agent should then possibly get some reward, or maybe no reward, depending on whether or not it was a good or a bad move. And of course, the state, if the system is observable, that the agent will be able to see what the new state it is in. And this can just go round and round and round and round until we finally get to a situation where we get a large cumulative reward. So let's think about what these terms actually mean. What is state, right? Well, it's basically what condition are we in at that particular time. I mean, people could be, you say to people, you're in a real state today. What you mean is you might look very upset, or you're aggravated or something, but state of a mind is also a state, happy, sad, and what have you. More specifically, in terms of the kind of thing we're interested in, it's basically the state of the system is how to describe the system in such a way that we can predict future behaviour for it. And most of you will have done control engineering, and we have state in that as well, right? We say, what's the state of the system, and then how can we update the state, with a state feedback control. What's the state of the system? So for a robot, it could be, the arm angles, the arm velocities. So the angles of the joints, or for example. So state is used by the agent, right? What state are we in now? We need to know that. The agent needs to know that so it can take the appropriate action. In a maze, right, the state would be something quite simple, probably just like, where are we in the maze? In an inverted pendulum, the state would be the angle of the pendulum to the vertical, and maybe its angular velocity, and maybe also the position of the cart. And this state then is basically something which captures pretty much everything you need to know about the agent's history. If it's a fully observable state, then the state of the system says everything about its past as well, so you can make a prediction in the future. And in the case of this simple pendulum, that would be theta dot x. Okay. So there are two different kinds of states as well. Of course, there's what state is the agent in, and what state is the environment in. Certainly, it's the environmental state that we're sort of relating to here, and when we're talking about pendulums, it was the state of the system, the state of the environment. The agent's just got to be able to read that and take advantage of it. But state is not always observable, so that it's sometimes, you don't necessarily, the system doesn't necessarily see all the variables. And then it's called, basically, an example would be partially observable Markov decision process. We will come back to that, right? And in this particular case, it means we can't see exactly what's going on. So, and again, we'll come back to that. So reinforcement learning then can also have a representation of the state of the environment that it can then act on. So really, it's the state of the environment and the relationship between the agent and the environment that we really care about, but we can't necessarily always see the whole state of the environment. Just like in control engineering, some systems are not fully observable. It's exactly the same idea. And it needs the state in order to be able to make the best next decision. So what's an action? Well, first of all, in the framework of reinforcement learning, we can either have a deterministic action, which is something we definitely do, or it could be that we have the probability of taking a particular action, and an action is basically all, what does the agent do? If it's stochastic, then when we're in a state S, we perform an action A, but this is going to then basically result in, we have a probability of performing an action A, and that results in a probability that we get to another state, right? So it could be that here is this is a stochastic policy, right? Our stochastic policy could be that when we're in this middle state here in this maze, 90% of the time we go straight up north, 3% of the time we go up at 45 degrees to the right. That's 3% of the time. 3% of the time we go 45 degrees to the left, and 1% of the time we just go completely to the right and 1% completely to the left. And with 2% of the time we actually stay where we are. So it could be that we have an action, which is basically in a maze it would be moving in a certain direction. If it's a stochastic system that we're in, we have a probability of taking an action, and if we have the probability taking action, that means there's a probability that we'll end up in another state. So what's the reward for a system? Well, reward is basically something you get for taking actions. In the case of capturing a criminal or something like that, you'd get if you take the actions you need to capture this guy, then the state would have given you $4,000 back then. It can also be the reward you personally get from winning a race, right? You've run a race you've run really fast and you've won the race. But it could also be a punishment, right? If you don't fill in your income tax returns properly, you might get a fine. That would be a kind of punishment for not taking the action that you needed to. So reward is indicative of performance at a task. That's the important thing. And generally speaking, we want to, we like some reward. We want to maximise. We want to make sure that when we're doing things, we're doing them with an end goal of getting a cumulative reward. Now, it doesn't have to be immediate. We don't, if we're moving around a maze, we don't need to get out straight away. We just have to move in the right direction. And then the last action will take us from inside to maybe outside, and then we're free. So it can be delayed. Examples of reward. So we can think of, how could we build reward in a robotics system? Well, imagine we're building a humanoid robot. If you manage to get it to walk, so it's moving forward, yeah, that's positive, right? So you've taken an action, it's moved forward. If it falls over, you punish it, right? We don't want it falling over, for sure. If you're playing a game of Noughts-and-crosses and you win, then you've got a positive reward. So all the actions you did in the state space that you were in at those particular times seems to be good. If you lose, then you did something wrong, then some of the action state relationships were not ones you maybe should have taken, right? And like I said, if you get to the goal in a maze. That's brilliant. You finally got there. You've got your reward value, and that's exactly what you wanted. Moving between non-goal states of the maze, that shouldn't be negative. That should be positive. Sorry, that's at least negative or maybe 0. Right? If you just move between 1 and 2, not very interesting. But if you move between 3 and R, you get your reward. If you wanted to say what's a reward for building a inverted pendulum, well, we'd say that if we imagine you're doing your controller and it's moving the cart backwards and forwards and it's looking at the state, if it manages to balance it, you've done an action and it's still balancing, excellent, that's a reward. If it falls over, no, that's a negative reward. Right, so it falls over. So policy then. What is policy? Well, I've already said policy specifies what is the action given the state, right? It defines, how the agent behaves. Policy is what we need to know in order to get the system to do something useful, right? So it could be that we're in a certain state, like the battery's charged up or something like this, in which case we can just stay in that state. If we then transition to the battery being in a low state, for example, then there's going to be a recharge path and all this kind of stuff. It basically tells us what we've got to do given the state we're in. And it can be deterministic, right? It can be that given the state that we immediately know we've got to take an action. For example, we could be in a maze and we're in state, let's say 3, and we know that the next thing we've got to do is to move north. But it can also be a probability, like I said. So we've got the probability of the action given the state. So it might be that 90% of the time we should move, let's say, north in a maze, but 10% of the time we should be moving south. So we can represent these deterministically or stochastically. So here's an example of a deterministic policy. So A is given by pi of s, in which case basically the policy returns the action we should take. So given that we're in state 1, we'd want to take action 1 with probability 1. So in other words, we want to take action 1. If we're in state 2, then we want to take action 2 with probability 1. And if we're in state 3, we want to take action 1 again with probability 1. So in this particular case, you could just write state 1, take action 1, state 2, take action 2, state 3, take action 1. And the reason that we've written it in this way is because we can see we have written it in a stochastic way, even though it's deterministic. So you see the sum across all the possibilities, right? So state, the action given the state sums to 1, because obviously the probability that you take an action has got to be 1, because you will take an action, but any specific action you take depends on the probability associated with it. Okay. Now, if we have a stochastic policy, what that means is we've got, in this case, slightly random values in there. In this case, it could be that, what's the probability of the action given the state? Well, if we're in state 1, let's say we take action 1 with probability 0.3 and a bit, action 2 with 0.36, action 3 by 0.31, if you round it up, action 4 with 0.017 and so on. So in this case, the most likely action we're going to take is number 2, and the most unlikely one is going to be number 4. But they're all probabilities, and we could actually, if we want to, we can easily implement that. We know how to generate actions with a certain probability using RAND, for example. In this case, though, we just note if we add up the probabilities for all the actions, so this 1, 2, 3, 4, they've obviously all got to add up to 1 because we've got to take some action. And the same thing for state 2. If we're in state 2, we get a different set of probabilities, and in state 3, we get a different set of probabilities. And like I said, because we have to take an action, if we take an action basically given the state, then overall the probabilities of the actions have got to sum to 1. Now let's consider a reinforcement learning maze task. The goal in this task is to move from the start to the goal. So we're in some start state. In this case, we're going to consider it as this green block here. We've marked it in. We see that we've got possible actions that we can take in principle, but they will depend on also what state we're in. So theoretically, if we're in the open, in fact, there's not really anywhere. This one's an example of an open state with all possibles, right? So you can if we're in state 85, we can go up to 95. We can go east to 86, we can go west to 84, and we can go south to 75. That's fine. If we were in a state like 72, obviously we can't go south, right? So in this case it's blocked because it's written in black, and we can't go east because it's written in black. And of course we can never go off the maze, right? So normally what we do when we're specifying what actions are allowed for a given state, we'd say that if you're going to hit the wall, you end up going back to where you came from. So 51 going west would stay in 51. Anyway, we've potentially got 4 actions. We start here in 1, and the idea is we'd like to maximize reward when we take a sequence of actions. And that's where we want to get to get there. We get some reward that's arbitrary. Now imagine we specify some random policy, right? Giving us the probability of choosing an action in a given state, right? So we could just randomly set that up using an appropriate random number allocation. But bear in mind, if we're doing a stochastic policy, for a given state, all the actions have got to add up to 1. So it could be that we do that, and what we do now, we're actually plotting out on these actual arrows what's the most probable action. But as you can see, they're not necessarily, actually they're not doing such a bad job, but basically these ones are not, that 4 is not pointing in a direction we'd want. If it was a really good policy, what we'd hope to happen is for every state, it would point us to get to the goal, right? These ones are actually quite good, 98 and 99. If we ended up here, we'd end up moving there and then there. So it's the actions here, given these states, the most likely actions are the ones we'd want. But generally, we don't know what the initial policy is because we've set it up randomly. So all we can do is just follow it and update it. So what we do is we'd start going to a state and then randomly choosing actions. Okay, like this, right? We'd randomly choose actions which were legitimate, like this, and see what happens from it. And in that way, we can actually learn optimal actions. And what we would do is we would update our policy. We will come to this in a lot more detail. This is just giving an overview. So finally what we do is we'd actually learn such that the probability, the most probable action given the state is one which is going to lead us all the way to the actual goal. So if we now look at, this has been run, and what I've done is I've run this probably using Q-learning. If let's say we started in state 1 now, we see the most probable action, and it could be 1, right? It could be a probability of 1, but the most probable action now is pointing to the left. So if we were in 1 and we took the most probable action, we'd move to 2. We see the arrows pointing to the right. We'd move to 3, and then we'd move to 4. Then from 4 we go to 14, 14 to 15, 15 to 16, 16 to 17, 17 to 18. Then we go all the way up here, and then we go all along here, and we'd end up in the goal. So after we've learnt the policy, we can just follow it, and it'll take us hopefully to the place that will maximise our long-term reward. And we do that in a maze task generally by getting to the goal state. There can also be multiple goal states. So having learnt it, then, just like I was showing you, we can just go to a state. And then just follow policy, right? So it'll take us from the first state to the second state. Then we look at the policy. It'll take us from this one to the next one, this one to the next one, just like I did now. I've just plotted them on top as being the optimal path by exploiting the policy rather than trying to do any more exploration. Now, in reinforcement learning. There is kind of two modes then that we need to actually use to actually get the thing to do what we want it to do. There's the learning phase, right, when we don't actually know the environment and we don't know the policies or the values of things, and we have to interact and we have to experiment and we have to get reward and use this reward to actually build up a better policy or a better value system. And just like I just showed you now, exploitation, this is then the planning phase really. This is when we've started to build up a model of our environment, and we can use it to actually make actions. We can also have another approach that actually really does have another model of the environment as well that completely is used to run over and over again, but we'll come to that later.